Suffix will be of two types, like primary suffix and secondary suffix. We will be discussing in detail what is primary and secondary suffix. Similarly, prefix comes before the word root. Bonding part. Okay. Suffix. Bonding part like what? Types like primary suffix and secondary. Okay, we will I will provide some overview. Okay, so let's begin. So you can see here, first of all, the word root. Word root is the basic unit of the name. As I told you already, it denotes the number of carbon atoms present in the parent chain, that means the main chain. What is a parent chain and how can we decide that this one is the parent chain or this one is not? So the longest possible continuous chain of carbon atoms, including the functional group and the multiple bonds of the organic molecules, that it will be the parent chain, and we will be discussing some examples and you will get a clear idea. Okay, so how can we decide what will be the word root? You can see some examples are there. If chain length is 1 carbon, then the word root will be meth. Chain length 2 carbon, eth. 3 prop, 4 but, 5 pent, 6 hex. Similarly, so on, 7, 8, 9, 10, 11, 12, like this. Okay, next you can see the types of carbon chain. Types of carbon chain can be of 3 types, like saturated, unsaturated, right? That means saturated containing single bonds only. So primary suffix we have to use ane. Primary suffix, what will be the primary suffix? Ane, and the general name will be alkane, and the general formula will be CnH2n plus 2. Okay, unsaturated with one double bond. Example, the simplest alkane is methane. The simplest alkene, this one is alkene, CH2 double bond CH2, and the suffix, primary suffix will be ene, and the general name will be alkene, and the general formula will be CnH2n minus 2. Okay, CnH2n minus 2 will be for alkyne, and CnH2n for alkene. And next one, unsaturated with one triple bond, that means the suffix will be ine and the general name will be alkyne, and the general formula will be CnH2n minus 2. So you can see here class of organic compounds like alcohol, and functional group is OH, and the secondary suffix basically represent the functional group. Okay, and primary suffix represent the types of bonding present between carbon and carbon atoms, like single bond present, so ane, double bond present, so ene, and triple bond present, so ine. Okay, you can see some examples like alcohols, suffix will be, secondary suffix will be ol, aldehyde al. Okay, ketones, it is one, one. Carboxylic acid, oic acid. Acetamides, CONS, this is secondary amide, and generally if I am writing primary amide, so it should be CONS2, this is an amide. Okay, COCl, oil chloride we have to use. For ester we have to use alkyl, then O8. O8 is the suffix and alkyl is the another part. We will be discussing that also. Okay, CN nitrile, SH thiol, NH2 amine, right? Similarly, like NC, it will be isonitrile, like this. Okay, let's continue with the primary prefix. Primary prefix is used simply to distinguish cyclic. So we have, as I told you already, we have 3 things: prefix, then word root, then suffix. Prefix 2 types, primary, secondary. Suffix 2 types, primary, secondary. Okay, in prefix we have 2 types, primary and secondary, and primary prefix basically distinguish cyclic from acyclic. This one is cyclic or this one is acyclic. You can just check this word. If cyclo is included, right? For example, in case of carbocyclic compounds, a primary prefix cyclo is used immediately before the word root. Thus, cyclo plus but plus ane. You can see this is primary prefix. Word root is but. But means 4 carbons are there, and in the parent chain, and ane means, ane is represent the between carbon and carbon there are only single bonds. That means primary suffix is ane. So cyclopentane will be the IUPAC name that is decided according to the International Union of Pure and Applied Chemistry. In the prefix, cyclo is not used. It simply indicates the compound is acyclic or open chain. If you are writing cyclopentane, it is cyclic. If you are writing only pentane, it will be acyclic or open chain. Okay, so primary suffix basically decide the types of bonding, and secondary prefix basically decide the primary suffix basically decide the types of bonding, secondary suffix basically decide the functional group type, and primary prefix basically decide the open chain or that means ring form. Okay, next one you can see here the secondary prefix. Secondary prefix will be the like any substituent, any other substituent like Br, NO2, any ethyl group, any ethoxy group, like this. Word root will be eth, primary suffix will be in, the name will be bromoethane. The name will be bromoethane, and because only 2 carbons are there and only 2 possibilities are there, and if I will attach the bromine here, definitely it will get number 1 position. We will be discussing what are the rules, right, to write the IUPAC name of any organic compounds. So we will be discussing that. Similarly, you can see nitromethane. Similarly, you can see ethoxyethane. This one is ether. This one is what? Ether ROR. Right? This one is ether ROR. In case of alicyclic compounds, primary prefix are also used. Next, IUPAC nomenclature actually is a set of rules established by the International Union of Pure and Applied Chemistry, as I told you already, for naming of organic compounds, right? For OC is not organic compounds. These rules are ensure a systematic and consistent naming system, right? If you are if you are writing methane here, if you are writing CH4 methane in one state, then in another state methane is still CH4, and in another country methane is still CH4, because it is internationally systemized. Okay, next point is here rules. The important part is here rules for writing the IUPAC nomenclature of organic compounds. So you can see, first of all, you have to identify the longest continuous chain. The parent chain should consist of longest continuous carbon chain in the molecule. For example, you can see here 6 members ring, right? You can see 1 2 3. I am not, you know very well, carbon can form 4 covalent bonds, so I am not completing the bonding part here, right? If suppose if I am writing like this, so you can see only 1 bond is made by this carbon, so you have to attach 3 other carbons or 3 other hydrogens or 3 other atoms. But if no other groups are there, so you have to attach hydrogen atoms always, right? So simply you have to attach 2 hydrogens here, simply you have to attach 2 hydrogens here, you have to attach 2 hydrogens here, like this you can complete it. So 2 bonds are there, so 2 more hydrogens, so 4 bonds completed. Similarly, 1 bond is here, so 3 hydrogens you have to attach. Okay, so you have to choose what you have to give numbering. You can see here 1 2 3 4 5 6 member ring. No, this is open chain. So 6 carbon chain, 6 carbon atoms are there in this parent chain. So this is what? Hex for carbon 6, for carbon 6 we have to use hex, word root, plus bonding part is ane, so the complete IUPAC name will be hexane. Like this we can write the IUPAC name. Next you can see here, this is hexane, 1 2 3 4 5 6. Next rule is the number the carbon chain in a way that gives the substituent the lowest possible number. Suppose I am removing this 2 and I am attaching any substituent like bromine here. Okay, so if you are numbering from here 1 2 3 4 5 6, similarly you can number from here 1 2 3 4 5 6. If the longest continuous chain, right, from left to right and right to left contains same number of carbon atoms, so you can see left to right 6 or right to left 6, right, then how can we prioritize which one is correct and which one is wrong? So the basic rule is that the lowest locant rule. That means the numbers given numbers to the carbon chain in a way, we have to give the numbers to the carbon chain in a way that gives the substituent the lowest possible number. And you can see the substituent is bromine here, so we have to give 3 or 4. So third one is this blue one, numbering is correct. Okay, this one is correct and the upper one is wrong, and this is wrong, incorrect. This is incorrect numbering. Okay, so 1 2 3 4 5 6, so it should be 3 bromo, right? This is prefix, bromo is prefix. Then word root should be hex, So we can write, and always when you are writing the nomenclature, so number and alphabets are separated by this hyphen, and if numbers are there, so you have to put a comma. Okay, you have to put a comma like this. Okay, so 3 bromo, then the word root will be hex, and the what I can say, the bonding part, that means the suffix, and that should be what type of suffix, primary or secondary, you have to choose, and it should be hexane. So 3 bromo hexane, right? Combine this name and you will get the answer. Okay, you can see here the next rule, identify and name substituents. Name then using prefix such as methyl, ethyl or bromo if any other. I told you already the examples, right? You can see to indicate multiple substituents. If more than one substituent is here, like you can see CS3, CS2, CS2, CH, CS3, then CS3 and CS3. So you can see if I am writing here CS3, CS2, CS2, CH, CS3, CH, CS3, CH3, like this. So you can see here, if I am doing numbering like this, 1, 2, 3, 4, 5, no, 5, yes, 6 or 6, both are 6, you can go anywhere, right? You can go straight or you can go below. Okay, then you can see if I'm doing numbering like this, 1, 2, 3, 4, 5, 6. So you can see if I'm moving left to right or right to left, which one is correct? Definitely right to left one is correct, because that means this color numbering is correct, because lowest position, because of lowest position. So you can see here the lowest position. Okay everyone, so you can see the groups are repeating itself, right? If they are different groups, suppose in one case this will be C2H5, right? We are not taking C2H5 because then it will be what, then it will become the longest chain. Okay, I will write another example. So you can see there are 2 methyl groups, so we have to write what, 2, 3 at position 2 and position 3. Locants are there. Locants mean the substituents. Okay, the substituent name is methyl, but they are 2 times, that means 2, 3 dimethyl. Then the word root, the prefix is completed, right? And this is not cyclic, so primary, secondary, both prefix is completed. Then word root will be longest chain is of 6 hex plus the carbon single, that means ane. So 2, 3 dimethyl hexane should be the IUPAC name of this compound. Write this. Okay, so next point is here, if there are functional groups present, they should be named and located using the lowest possible numbers, right? So if functional groups are there, similarly you have to follow the same pattern. You have to give number 1 here, number 1, 2, then 3. This is longest chain. Okay, this should be like this. Okay, CHOH and CS3, CHOH and CS3. If I am removing from here, then you can see 1, 2, 3, 4, 5, 6. Okay, and write the name, write the name of IUPAC name according to alphabetically rules. Okay, so this is a functional group. Okay, and this is a what, substituent. So you have to write 4 methyl. What will be the name? 4 methyl. This is prefix. Then word root will be hapt, 4 methyl hapt. Then you can see here the functional group is what, OH. For OH we have to use the suffix ol, and it is the secondary suffix. So what is the primary suffix? The bonding part, and bonding is only single here, so ane plus what is the position of OH? Second, so 2 ol, but they both are vowels, so you have to remove this vowel. Okay, so the complete name will be 4 methyl hapt ane 2 ol, like this. Okay, so let's continue to the next. Double bonds are indicated by the suffix "-ine", and triple bonds are indicated by "-ine", and single bonds are indicated by "-ane". Okay, so you can see here the position of the bond is indicated by the lowest possible number always. Suppose you are saying 1, 2, 3, 4, 5, this blue one, and the next one is what, this one. You can see here, if I am saying 1, 2, 3, 4, 5. So you can see here this numbering is correct, this is incorrect, this is incorrect. Okay, why? Because double bonds lowest number. Okay, you can say lowest possible number. We have to go, we have to give multiple bonds, double bond, triple bond, functional groups like this, or substituents like this. Okay, so the name of this what compound will be, no prefixes here, only what, word root. So word root is pent, Similarly, suffix is here. Suffix is what? In, not in. Okay, so pent, what is the position of suffix? To. So pent to in, like this. Okay, pent to in. Okay, so let's go to the next. So pent to in. For cyclic compounds, use the prefix cyclo. For example, if any cyclic compound is here, like this, suppose this is the cyclic compound, 6-member ring is here. So this is cyclic 6-member, and so you have to use cyclo and then write the nomenclature for normal compounds like hex and ane. So it should be cyclohexane. Similarly, cycloheptane, cyclopentane, like this. Okay, then summary points. The basic rule for the nomenclature, I told you already. Prefix, word root and suffix, they are important. Prefix and suffix are of two types, primary and secondary. Okay, you can see organic compounds like double triple bond containing like this, alkene, alkyne. Halogen derivatives like X should be fluorine, chlorine, bromine, iodine, and haloarenes like C6H5X. Oxygen containing compounds like alcohols, ether, carbonyl compounds, right? Carboxylic acid derivatives like ester, amides, anhydride like this. You can see R, C double bond O, O, C double bond O, R. R dash may be same or may be different. Similarly, you can see carbonyl compounds, aldehyde and ketones. Similarly, you can see amines like primary, secondary and tertiary amines. Nitro compounds like RNO2, cyanides like RC, and isocyanide like RNC. This is the summary points. Now you can see IPC nomenclature of alkanes, straight chain compounds, right? You can see the name of such compounds are based on their chain structure and end with suffix "ane" and carry a prefix indicating the number of carbon atoms presenting in the chain except from CH4 to C4H10, where the prefixes are derived from their trivial names. Okay, so you can see like IUPAC nomenclature, some of the unbranched saturated hydrocarbons like methane, ethane, propane, butane, pentane, hexane. You can see some examples and their molecular formulas, right? Similarly, you can see some alkyl groups like you can write CH3 like methyl, right? You can see methane to methyl, ethane for ethane. If I am removing, you can see here the general formula of alkane is CnH2n plus 2. If you will remove one hydrogen, you will get CnH2n plus 1. So this is what? This is the general formula for alkane, and this is attached to any other carbon chain, right, or group, right? So this is alkyl. This is what? Alkyl. Okay, like CH3 is methyl, like C2H5 is ethyl, like C3H7 is propyl, because C3H8 is propane, like this, etc. Okay, I hope this is clear. Let's move to the next one, branched chain hydrocarbons. If any branching is here, so you can see there are two numberings. So first of all, find the longest chain in the molecule. So you can see 1 2 3 4 5 6 7 8 9. Similarly 1 2 3 4 5 6 7 8. So this is the longest chain, and it includes one or two groups, or it includes one or two groups. So both includes two groups, but the longest chain is of 9 carbons. Okay, so like this you have to choose the nomenclature. Okay, you have to choose. The numbering is done in such a way that the branched carbon atoms get the lowest possible number. So 1 2 3 4 5 6 7 8 9, you can see 2 here. If you will do the numbering from right to left, so 1 2 3 4, so this is ethyl, this is ethyl, this is methyl. Okay, if you will attach the 3 hydrogens, and similarly you will complete the bonding of this these two carbons. Okay, this is again methyl and this is ethyl. So you can see 2 is the lowest possible number which is assigned to the nearest group. Okay, so you can see the names of alkyl groups attached are indicated by the appropriate numbers. Like you can see these groups, right? You can see you have to learn these groups. Okay, these groups, when a carbon is attached to two methyl groups, you can see this is named as isopropyl, and this group is attached, this second carbon is attached to any other group. Like suppose I am writing CH3 CHOH CH3, so this will be isopropyl alcohol. Suppose I am writing CH3 CH Cl CH3, this will be isopropyl chloride, like this, right? You can see second carbon, right? You can see this is the 1 2. If second carbon is attached to what, any other group or any other chain, then this is commonly named as sec-butyl. Similarly, you can see isobutyl. Similarly, you can see tertiary butyl and neopentyl. If you will attach the hydrogen here, it becomes neopentane, like this. Okay, so let's move to the next. If two or more identical substituents are present, right, so the numbers are separated by commas, and as I told you already, you have to use di, tri, tetra, penta, hexa, like this. While writing the name of the substituents in alphabetical order, these prefixes are not considered, right? So you can see here this is 2 and 4, so 2 comma 4 dimethyl pentane. Similarly 1 2 3 4 5 2 comma 4 2 comma 2 comma 4, it should be CH3. So 2 comma 2 comma 4 trimethyl pentane. Similarly you can see 1 2 3 4 5 6. So this is ethyl, this is methyl, this is methyl. So first of all you have to write ethyl. Okay, so 3 ethyl 4 comma 4 dimethyl heptane. If two substituents are found in equivalent position, so it is at 3. If you will do the numbering from here, so it is again at 3. So you have to follow alphabetical order. So what are the basic rules? First rule, longest continuous chain. If you are not able to find the longest continuous chain, that means from left to right, right to left, the longest continuous chain is same, right? So same number of carbon atoms, include same number of carbon atoms, then you can go to the next one, that is the lowest locant rule. Okay, and the third one will be the alphabetical rule, right? Like if the two substituents positions are found in equivalent position, that means the lowest locants are same. So you have to you have to give the lowest number to that one according to alphabetically. Okay, so you can see this is methyl and this is ethyl. So if you will do numbering from here, that means right to left. So methyl comes at third position. If you will give numbering left to right, so ethyl comes at third position. Definitely E comes first, right? Dictionary rules you have to apply. So E comes first. So definitely you can write the name according to that position, right? According to that alphabetical order. So 3 ethyl. What will be the IPS name? 3 ethyl, 6 methyl. And then prefix completed, word root is oct, then suffix will be ane. Okay, so 3 ethyl, 6 methyl, oct ane. Let's move to the rule number 6. The carbon atom of the branch that attached to the root alkane is numbered as 1 always. You can see 1 2 3 4. Suppose any group is available here and this is the longest chain, right? And this group is attached here. So always you have to provide number 1. You have to assign number 1 to this carbon which is attached to the parent chain. Okay, always. Okay, so this is, so you can see here this is attached to the any other carbon chain, and 1 2 3 4 like this. We have to assign number 1 always to the carbon which is attached to the main chain. Okay, that is the point. Let's move to the rule number 7. While writing the trivial names of the substituents in alphabetical order, like I told you for iso, sec and neo. So iso and neo are considered to the part of the fundamental name of alkyl group, but sec and tertiary are not considered. Okay, so you can consider iso and neo as an alphabetical order, like to decide the alphabetical order. But if the name is like sec butyl, sec pentyl, so sec and tertiary butyl are not considered to the part of the fundamental name. You can see here, this is an example like 1 2 3 4 5, and we have done with the example. Okay, so you can see the name is 5. At 5 you can see always give the first number to that carbon which is attached to the main chain. So 1 2 3 4. At 5 you can see use a bracket if a complex, this is the complex substituents, if a complex substituent is available. So 5 dash 2 dash ethyl butyl, right? Because this is also a part of the main chain, that's why we have to use the word butyl, not butane. Okay, so 5 dash 2 dash ethyl butyl, then 3 comma 3 dimethyl. You can see here 3 comma 3 dimethyl, and 10 carbon dec plus n decane, not 5 dash 2 comma 2 dimethyl. Okay, because you can see this is D and this is E, and we are not considering D tetra while writing the name, right, in alphabetical order. Okay, similarly you can see 5 sec butyl. So you can see this is sec butyl. Sec butyl and tertiary butyl are not considered. Okay, so we have to consider this B. Okay, so 5 sec butyl, but iso is considerable. So 5 sec butyl 4 isopropyl decane, this is the name. Let's move to the rule number 8. If there happens to be two chains of equal size, then that chain is to be selected which contains more number of side chains. Okay, after selection of the chain, numbering is to be done from the end closer to the substituent, right? I will go to the cyclic compounds, but before that I want to give some examples. Like you can see carbon 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 carbon, right? If there is a, my point is here, if there is a group, right? Similarly carbon, then there is a carbon CH3, right? Or you can write CH2 CH3, then CH3. Okay, so you have to choose first of all longest chain, then lowest locant. But the point is here, if you will choose any carbon chain, and suppose left to right and right to left the carbon chain, or any suppose you are finding two numberings in that particular structures, and you can see like both numberings are of both numberings included 10 carbons, right? 10 carbons. Then you have to choose that particular chain which includes more number of side chains, more number of side chains, more number of side chains. Okay, you can see in the previous example, you can also understand this point. Suppose you are choosing the nomenclature of this 1 2 3 4 5 6 7 8 9 10, 10 carbon, but we have to choose 1 2 3 4. Why? Because it includes, you can see at third position, then third position, then 5 position. So 3 groups are there. Total number of side chains, total number of groups, side groups are 3 here. But if you will choose this straight chain, then you will get only 1 and 2 groups are there. Like these two groups include same number of carbon, right, or different number of carbon, that no, doesn't matter. The part is here, like this straight chain includes lesser number of side chains. That's the part. Okay, so that's the point number 8. Let's move to the cyclic compounds. Same, you have to use the cyclic word, cyclopentane, and then you can use alphabet order of numbering 1 2 3. So 1 methyl and 3 propyl, 1 methyl 3 propyl cyclohexane. You can see 1 comma 1, more branched carbon gets lower number, definitely lowest locant, right? So 3 ethyl 1 comma 1 dimethyl cyclohexane, not, so the lower one is wrong. Okay, nomenclature of organic compounds having functional groups. So first of all, the longest chain of carbon atoms containing the functional group. So you have to choose the longest chain which includes the functional groups along with the multiple bonds. Okay, and functional group is attached at the carbon atom possessing lowest possible number. That is the point. Okay, second rule is also. Second point, in case of the polyfunctional group compounds, one of the functional group is chosen what as the principal functional group. Okay, principal functional group, and the compound is then named on that basis. The remaining functional groups which are subordinate, what I can say functional groups, are named as substituents. Okay, suppose the principal functional group is COOH and the other functional groups like OH is here, CHO is here. So these are side groups, or these are considered as substituents. The main group is this. That means suffix, secondary suffix of this COOH is used only, not for OH and CHO. For OH and CHO we have to use prefix. Okay, the choice of the principal functional group is made on the basis of this order. You can see the order will be the order of decreasing priority for some functional group, like the prioritized group is COOH, which is carboxylic acid, then SO3H, then COOR, R is alkyl group here, then COCl, then amide, then CN, then HO. This is alcohol. Okay, OH is alcohol, then C double bond ketone, right? Okay, this should be CHO. Okay, this is aldehyde. Okay, aldehydes are more prioritized than ketones. Okay, this is ketone, aldehyde, then ketone, then alcohol, then NH2, then C double bond O, and then C triple bond. Okay, so double bond is prioritized, then triple bond, it should be mandatory. Okay, the R, CH5 halogens, these are points here, are always substituents, like R group, which is an alkyl group. C6H5 is like C6H6 is benzene, but C6H5 is phenyl. When when benzene act as substituents. Halogens like fluorine, chlorine, bromine, iodine, and NO2 group, NO2, and alkoxy group, which is like a methoxy, ethoxy, like this. These groups are always act as a substituent. Thus, a compound containing both an alcohol and a group is named as a hydroxyalkanone, since the ketone, like alcohol and a ketone group, right? Since the ketone group is preferred to the hydroxyl group. Next point, if more than one functional group of the same type are present, and one more point you can see here, if you want to check, the point is here, if more than one functional group of the same type are present, their number is indicated by adding di, tri, etc. before the class suffix. In such cases, the full name of the parent alkane is written before the class suffix. For example, you can see CH3, CH2OH, CH2OH. So you can see this is CH2OH, CH2OH, 1, 2. So 2 carbons are there. Word root is it. Suffix, like you can see, suffix is ane. Then there should be one more suffix which represents the functional group. So ethane 1, 2 di diol. Ethane 1,2 diol. Okay, but you can see this is not a vowel, so we have to use this E. Okay, this should be mandatory. Okay, I hope you are very much clear. However, the ending Ne of the parent alkane is dropped in the case of compounds having more than one double or triple bond. For example, CH2 double bond CH single bond CH double bond CH2 is named as buta, not butane 1,3 diene. Okay, so if more than one double bond or triple bonds are there, so you have to drop this ane part. Okay, Ne part from this ane. Okay, I hope this is clear. Let's move to the nomenclature of substituted benzene compounds. If benzene ring is disubstituted, okay, the position of the substituent is defined by numbering the carbon atoms of the ring such that the substituents are located at the lowest possible numbers. Again, you have to follow the same rules. Longest chain, longest continuous chains includes functional groups, and what I can say includes functional groups and multiple bonds. Then go to the lowest locant, third alphabetical order. Like this is methyl benzene and also commonly named as toluene. This is methoxybenzene commonly named as anisole. Similarly, the next one is aniline, right, and aminobenzene. Next is nitrobenzene and bromobenzene. I hope this is clear. Next, you can see in the trivial system of the nomenclature, the terms ortho, meta and para are used. What is ortho, what is para, what is meta? So you can see ortho, meta and para are respective positions, right? Suppose this benzene is attached to any group, right, G. Okay, so with the respect of this G, this position is ortho position. With the respect of G, this position is meta position and this position is para position. That means you can say this is 1, then this is 2. So 1, 2 position is ortho position, 1, 3 position is meta position, 1, 4 position is para position. Then again this comes 1 and 2 and 3. So this is again ortho position, this is a meta position and this is para position. So with the particular group, if a single group is present on benzene ring, then there are 2 ortho position, 2 meta position and 1 para position. Like this you can say. One more point I want to tell you. If the group is present here, this is benzene ring. If the group is present here, suppose CH3, then this is not at meta, not para, not ortho position because no reference is here, right? If the group is OH is available here, then these two groups are related. 1,3 position definitely are related by 1,3 position. So they like with the respect of OH group, CH3 is at meta position of phenol. That means OH. Okay, that's the point here. I hope you are very much clear about ortho, para and meta. So similarly, you can use this numbering like 1,2 dibromobenzene, or also you can say ortho dibromobenzene. Similarly, 1,3 dibromobenzene or meta dibromobenzene or para dibromobenzene, like this. Okay. In some cases, common names of benzene derivative is taken as the base compounds. Like you can see 1-chloro 2,4 dinitrobenzene, not 4-chloro 1,3 dinitrobenzene, because of what? Substituent of the base compound is assigned number 1, right? So you can see 1-chloro 2,4 dinitrobenzene. So nitrobenzene is taken as a base compound. So benzene derivative is taken as a base compound. So we have to provide what I can say. So you can see here substituent of the base compound is assigned number 1, and then the direction of the numbering is chosen such that the next substituent gets the lowest number. Okay, so you can see this is the part. The substituent appear in the name in the alphabetical order also, and you can see some examples. I hope you are very much clear with these examples. Okay, you can see like this. OMe, Cl, and so anisole. This is anisole. With this anisole, right, while writing the nomenclature, it should be 2-chloro 4-methyl anisole, like this. Okay. Similarly, this is aniline. So we have to provide number 1 to this. Okay, we have to provide number 1 to this substituent. Okay, substituent of the base compound. I hope this is clear. Let's go to the IUPAC nomenclature of bicyclic compounds. Identify the longest chain, right? Bicyclic compounds means 2 carbon atoms are common, right? And you can see here longest chain in the molecule that contains the bridgehead carbons. Number the bridgehead carbons as 1 and 2 in the direction that gives the lowest possible number to the substituents. Count the total number of the carbon in the bridge and assign the appropriate bicyclo prefix. Use the prefix bicyclo followed by the number of the carbons in the bridge followed by word "ane" to indicate that the compound is a saturated hydrocarbon. That's very simple part. Okay, I will discuss some examples. At the locale, multiple substituents, arrange them in alphabetical order. If you want to see some examples, I will provide some examples to you which are very simple. You can see some examples, like first of all, let's see the point number 8 and 9. Separate the locants and substituent names with hyphens, definitely, and enclose the full name of the compounds in parentheses after the substituent name. So you can see example like bicyclo 3, 1, 0, bicyclo 3, 1, 0 hexane. Okay, 3.1.0. You can see here in this example we have a bicyclo compound with a bridge consisting. So you can see this is the, these are what, bridge head. Okay, you can see 1, 2, 3 carbons are there, and actually 2 rings are there. One is a 5 member, one is of 3 member, and they are fused like this. Okay, so there are 2 common carbons, right? These are this is common between this 5 and 3 member ring, and this one is also common. Okay, so you can see the left one includes 3, the right one includes only 1, right, and 2. So you can see in this example we have a bicyclo compounds with bridge consists of 3 carbons and no substituents. Therefore the name is bicyclo 3.1, and bridge has no carbon, so .0. Okay, so 3.1.0 hexane. I hope this is clear. Let's move to the next one. IPC nomenclature for Spiro and bridge compounds, right? For Spiro and bridged compounds. So you can see Spiro compounds. Spiro compounds are cyclic compounds that contains 2 or more rings, share only 1 common atom. In the previous one, bicyclo, 2 common atoms are there, and in this case, Spiro, only 1 common atom is there, right? But it can also be nitrogen, oxygen, or sulfur, not only carbon. You can see the example here. The example, okay? So this is the example, like 1 common atom. This is the common atom. Okay, 1 2 3 4, 1 2 3 4 5, like this. So you can see in this ring 4, in this ring 5, right? Atoms are there. So what should be the name of this one? So I want to provide some examples. This one is Spiro. How can you write? Spiro 4, 5 decane. Total 10. Okay, total if you want to count, you can see 1 2 3 4 5 plus 4 9 plus 1 10, so total 10. So decane and 4 4.5. okay, you have to use bracket as well. Spiro square bracket 4.5 decane. Next, bridge compounds. You can see here bridge compounds are cyclic compounds that contains 2 or more rings that are connected by a bridge made up of only non-ring atoms. Example, decalene. So this one is what? Decalene. You can see again 2 common atoms are there. Let's move to the next one. Bridge compounds. IPC nomenclature for bridge compounds involves indicating the bridge head atoms, which are the atoms where the bridge connects to the rings. Okay, the bridge head atoms are numbered with a prime symbol dash, like this. So 1 dash, 2 dash, dimethyl bicyclo 3.1.1 heptane. Okay, like this you can provide. So how can you write this? Like what are bridge head? Like this you can write. Like this. Okay, so bridge head carbon. This is the bridge head carbon. This is the bridge head carbon. Okay, this is the bridge head carbon. Includes. I hope this is clear. Let's move to the next. Covalent bond fission. That means we are discussing homolytic and heterolytic fission. First is homolytic, the next one is heterolytic. In homolytic fission, you can see it refers to the breaking of a covalent compounds. You can see like Rx. Okay, so it's like this. We are providing heat or light. And then suppose as hydrogen and hydrogen is here, so it will form free radical. That means the 2 electrons are present in a single bond and they will go to the each electron. So 1 electron go to the each atom. Okay, you can see each bonded atom retains one of the shared electrons, resulting in the formation of 2 radicals. Okay, so homolytic fission is represented by single headed arrow, or you can say fish hook arrow. Okay, hetero means like different, definitely. One is more electronegative, another is less electronegative atom is here. So breaking of a covalent bond where one bonded atom retains both of the shared electrons, resulting in the formation of 2 ions. Suppose I am saying A and B bond, right? So I am saying B is more electronegative than A, then both electrons will go towards the B and it will form B negative and A positive, right? Because A loss of electrons and B gain of electrons. The atoms that retains the electrons becomes negatively charged and forms a negatively charged ion, that is known as anion. So B is anion here, and the atoms that loses the electrons becomes positively charged and forms a positively charged ion, that is known as cation. Heterolytic fission is represented by double-headed arrow, right? You can see double-headed arrow. Okay, then electronic displacement in a covalent bond. So we will be discussing inductive effect, mesomeric effect, right, and electromeric effect and hyperconjugation. So let's understand. So the inductive effect is a concept in organic chemistry. So first of all, electronic displacement, like you can see na, electronic displacements, if there is a bond like between A and B, so electronic displacement will takes place, right, in a covalent bond. If two electrons can go one electron to each atom, similarly both electrons can go to the single atom. That depends on the homolytic or heterolytic cleavage. But the part is here, there are four effects. Inductive effects is a concept in organic chemistry. It is a permanent effect. It is a permanent effect that describes the electron donating or electron withdrawing nature of the substituents on a molecule. If I effect, okay, inductive effect is usually measured the ability of a substituents to donate or withdraw electrons density through sigma bonds. That's why it is a permanent effect. Okay, it occurs when there is a electronegativity difference between the atoms. Okay, suppose I am attaching carbon to NO2 and there is a carbon chain, and this is the end of the chain like this. Okay, so this NO2 group is between this carbon and nitrogen. Thus covalent bond is here, and nitrogen is more electronegative than carbon, so definitely it will show its electron withdrawing nature, and this is minus I effect. This is minus I effect. Similarly, like R group will show plus I effect, R group can show plus I effect. So you can see types of inductive effect. There are two types of inductive effect. One is electron donating group show plus I effect, and electron withdrawing, that means EWG, will show minus I, and EDG will show plus I effect. Alkyl groups like methyl, ethyl are electron donating, and as the number of alkyl groups increases, electron donating groups like increasing, definitely plus I effect increases. Okay, so you can see they are electron releasing alkyl groups. So amino like NH2 group are also electron donating due to the presence of a lone pair on the nitrogen atom like this. Electron withdrawing EWG group show minus I effect, right? This is the, suppose this is the ring, or this is the main chain. If we are withdrawing the electrons, so definitely it is minus I. If we are providing the electron, it should be plus I. Nitro group nitro groups are electron withdrawing group due to the presence of the electronegative nitrogen and oxygen atom. Similarly, carbonyl, if C double bond O groups are there, right, attached to like a ring or any other chain, they will show plus I or minus I effect. That means they are electron withdrawing group due to the electronegativity difference between carbon and oxygen. So the inductive effect can affect various properties of organic compounds such as acidity, basicity and nucleophilicity. Now the next point is electromeric effect. So we have discussed inductive effect, and they are of two types, plus I effect and minus I effect. Similarly, electromeric effect are of two types, plus E effect or minus E effect. The point is here, that is very simple. Electromeric effect is a temporary effect. Inductive effect was a permanent effect. Electromeric effect comes into play when like what is the electromagnetic? First of all, let's understand. This is the movement of electrons in a pi bond or a lone pair of electrons in response to the attack of an electrophile or nucleophile. So there is a substrate, like suppose this is the substrate. If any electrophile or nucleophile will come, right, if any electrophile or nucleophile will come, then electromeric effect arises, otherwise not. That means this is a temporary effect, right? This comes into play when there is an attacking species. Okay, it leads to the formation of a new covalent bond. So let's understand the plus E effect. Plus E effect, it involves the movement of electrons towards the attacking electrophile. Electron donating group facilitate the formation of a new bond. That is the point here. Okay, so suppose CH2 double bond CH2, or any electrophile is attacking here like H positive, so this is the attack, right? The electron density, that means pi bonds to electrophile. So it involves the what I can say, it involves the movement of electrons towards the attacking electrophile. So what you can understand from this, you can see, suppose CH2 double bond CH2, suppose this bond is going here. So for example, okay, let's imagine this point, then it will get negative and it will get positive charge, then definitely H positive will attached here, right? So electron density is moving from center to right side, and electrophile is also attaching to that particular carbon which is getting the electron density, right? So if electron density movement, right, and the attacking of, what I can say, and the attaching of electrophile to the same carbon to the same atom, that is plus effect, like this. If suppose CH2 double bond CH2, if nucleophile comes, and suppose this is moving like this, negative, so nucleophile will attack to this carbon because it will get positive. So electron density is moving right side, but the nucleophile is attaching to the other carbon, not that particular carbon which is getting the electron density, right? So my point is that you can understand like this. How can you learn plus E or minus E effect? In case of electrophile, it is plus E. Electrophile, positively charged, plus E. In case of nucleophile, it is minus E, like this. Okay, I hope you are getting negative, negative. Let's move to the next. Minus effect involves the movement of electrons away from the attacking electrophile, right? Away, and in this case towards the attacking. Okay, electron withdrawing groups hinder the formation of new bonds. Examples of electromeric effect, like you can see, plus E effect alkene, OH, OR, minus E nitro group or CN. Next is resonance. This is also named as mesomer effect. Introduction. Resonance is a phenomena where the delocalization of electrons occurs across multiple atoms or molecules. It stabilizes the molecules by distributing the charge of electron density over a larger region, right? Suppose if I am writing here, this is a benzene and this is O negative, so this is phenoxide ion. So this phenoxide ion is not stable. So what is this doing? This is like this. This is the electronic displacement, right? So what will happen? There will be double bond. The bond comes here. This is this, and then what happens? Not positive. It should be negative. Okay, like this. Then this comes here, and this is. So this is the resonance, and it is represented by a double arrow, right? You can see double-sided arrow, and this is double bond O. Then this should be negative. Here should be double bond and double bond. Similarly, the next step will be like this, and double bond O, then double bond, and it should be negative and double bond. Then again you will get the first structure. So these are resonating structures. Okay, so this negative charge which is present on oxygen atom, and now again oxygen atom is getting the negative charge after some time. That means it becomes stable. Okay, like this. So next you can see resonating structures are different Lewis structures that can be drawn for a molecule or an ion, right? They only differ in the arrangement of electrons. Only arrangement of electrons or the formation of bonds between the atoms is different. It's different means formation of bonds, like the bond is formed. First the bond is found between double bond is found between 1 and 2 carbon. Next time the double bond is found between 1 and 2, no, like this. Okay, but the total number of bonds, total charge, and everything remains same. Everything remains same. So you can see here the what I want to say, that can be drawn for a molecule or an ion. They only differ in the arrangement of electrons, but have the same overall connectivity of atoms. Connectivity should be same. Resonance stabilization lowers the overall energy of molecule or ion and increase the stability. If energy is less, definitely more stability, and decreases the reactivity. Okay, examples like benzene ring, as I told you already. In this case, like benzene ring, these are like calculus structures. This will go here, then this is, and this is. So you will get this like this, and this one and this one. Okay, these are like calculus structures. Then similarly NO3 negative nitrate ion. What is hyperconjugation? Hyperconjugation effect. Hyperconjugation is the you can see here, hyperconjugation is the delocalization of electrons from a sigma bond to an adjacent empty or partially filled orbital. It stabilizes the molecular ion by increasing the electron density around the carbon atom, right? You can see the key points of hyperconjugation. Stability. Hyperconjugation increases the stability of the molecular ion. Definitely it will increase the stability of the molecular ion. It is more prominent in carbocations and free radicals. Effect on reactivity. Hyperconjugation can increase the reactivity of a molecule by stabilizing the transition state. Okay. Stability of alkyl carbocations, stability of alkyl free radicals, tertiary carbocations are the most stable, followed by the secondary and primary. Stability increases with increasing substitution. You can understand hyperconjugation effect like this. Carbon, and it should be like 3 hydrogens, then CH2 positive. You know very well, CH3, CH2 positive. And in this CH2 positive, there should be empty orbital like this. Okay, there should be empty orbital like this. Suppose there is a double bond as well. So I can write like this: CH3 CH double bond CH2 CH positive, double bond CH positive. Or you can write like in simple words. Let's take simple example: CH3 CH2 CH positive, CH2 positive. Okay, so you can see this is alpha carbon, this is beta carbon. Okay, so alpha carbon has two hydrogens, but if you can see, if I will attach this CH2 positive directly to this CH3, so it will have three hydrogens. So definitely three hydrogen means it will be more stable. Then so more the number of alpha hydrogens, more the number of hyperconjugating structures, and more will be the stability, like this. Okay, so this is the hyperconjugation. Next is reactive intermediates. What about reactive intermediates? You can see introduction of carbocations. Carbocations are organic ions where a carbon atom has a positive charge, and they are also known as carbonium ions. Like I have drawn CH3 positive, this is methyl carbocation, like this. Structure: carbocations have an empty p orbital on the positively charged carbon atom. I have drawn the p orbital, which makes them electron deficient. The carbon atom is sp2 hybridized with a trigonal planar geometry, like this: C positive. Suppose this is CH3, this is CH3, this is CH3. So this should be tertiary butyl carbocation. This should be tertiary butyl carbocation, and the hybridization of this carbon is sp2. Right? You can see the structure here. And this is the empty orbital. There are 3 sigma bonds, 120-degree angle, and sp2 hybridized carbon orbital, and this is the structure of carbocation. Stability of carbocation. Carbocation can be classified as primary, secondary, or tertiary based on the number of carbon atoms bonded to the carbocationic carbon. Right? So stability order must be primary, secondary, or tertiary. You can see this is the C positive, then CH3, then CH3, then CH3. Okay. Then next one is C positive, then CH3, CH3, and hydrogen. CH3, hydrogen, and hydrogen. This is, you can see here alpha, 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 alpha. So total 9 alpha hydrogens, total 6 alpha hydrogens, total 3 alpha hydrogens, and there is no alpha hydrogen. So no hyperconjugation in case of CH3 positive, which is less stable. Then stability increases like this if the number of alpha hydrogen increases due to the hyperconjugation effect. Due to hyperconjugation effect. Okay, I hope this is clear to you. So that will be the stability order of carbocations, and this carbocation, right? The carbocation which is the carbon which is bearing positive charge is attached to only one what I can say hydrogen, or you can say if only attached with 0 hydrogens and 3 R groups, 3 alkyl groups, then it is named as tertiary. If 1 hydrogen and 2 alkyl groups, then it is named as secondary. If 2 hydrogens and 1 alkyl group, then it is named as primary, and this one is last one is methyl carbocation. Then you can see carbon ion. Carbon ion is an organic ion in which a carbon atom has a formal negative charge, like CH3 negative. This one is methyl carbon ion. It is a type of reactive intermediate in organic chemistry, and carbon ion are formed by the loss of proton from a carbon atom. Structure of carbon ion I will be discussing, but you can see they have a pyramidal or trigonal planar geometry, right? They have a trigonal or planar geometry. The carbon atom with the negative charge is sp2 hybridized, resulting in a trigonal planar geometry. Okay. You can see here C and H, H, and H. So sigma, sigma, and sigma, like that. Due to the presence of lone pair of electron, it may exhibit a pyramidal geometry as well. Okay, so you can see here the structure. This is the pyramidal geometry, but the this is the pyramidal shape, but the geometry will be tetrahedral. Okay, and this is sp3 hybridized orbital. Okay, this is sp. The carbon atom with the negative charge is sp3, not sp2. This is sp3 hybridized, because you can see while calculating the hybridization, you know very well you have to count the sigma bonds, then you have to count the lone pair which is not participating in the resonance. So definitely this lone pair is not participating in the resonance. So sigma, sigma, sigma. So 3 sigma plus 1 lone pair, so 4, and you have to give 1 s and 3 p. So sp3 hybrid orbital. Right, this is the structure of carbon ion. In this is not a planar geometry, this is a pyramidal shape. Okay, Stability. Carbon ions are stabilized by electron withdrawing groups or by resonance. Alkyl groups attached to the carbon ion always stabilized it by donating, electron donating, right? Order of stability. Primary carbon ion are more stable than secondary, then tertiary. Okay, primary carbon ion, right? And you can see here the next point is here radical. Okay, I hope this is clear. And one more point I want to tell you. Suppose CH3, C, CH3, CH3 and negative. So this carbon ion is not very much stable, right, as compared to this one, because due to, you can see, hyperconjugation will take place. Okay. I have to attach hydrogen here, hydrogen. Okay, and it should be negative. Like this is tertiary carbon ion, this is secondary carbon ion, and this is benzyl carbon ion, CH2 negative, CH2 negative. This negative goes comes here, then resonance will take place like this. Okay, next is radicals. Okay, so we have discussed carbocations, carbanions, reaction intermediates, and now we are going to discuss radicals. Radicals are odd electron species and they are highly reactive species that contains unpaired electron. They are found by homolytic cleavage. We have discussed already, like suppose Cl and Cl, if I will provide heat and light, so the electrons goes like this and you will get 2 Cl radical. Okay, the shape and structure of radicals plays crucial role in determining their stability and reactivity. Factors, those factors which are affecting the stability of radicals are what? Like alkyl radicals are classified as again primary, secondary or tertiary. Alkyl radical stability increases as we proceed from primary to tertiary. So methyl radical, then ethyl, then isopropyl, then tertiary butyl radical. Like this is the stability order. Let's discuss electrophile and nucleophiles. Okay, electrophiles. Electro means electron and 5 means loving. So electron loving species are known as electrophiles. They may be neutral or they may be what? Positively charged. So electrophiles are positively charged because they are like electron deficient, right? So electrophiles are electron deficient species that can accept an electron pair from a nucleophile. Like H positive is an electrophile, like Cl positive is an electrophile, like OH positive, right? So they are often positively charged or have a partial positive charge. Electrophiles are attracted to the what I can say, to regions of a high electron density, right? Example of electrolytes includes carbocations and positively charged ions. Electrophile can be neutral as well, like incomplete octet, for example BF3, like Lewis acids AlCl3, like okay, like AlCl3. So that's a point here. Let's move to the nucleophiles. Nucleophile means, nucleo means positive, phile means loving. So positive loving, that means nucleus loving species. Nucleophiles are, nucleus loving means they have electron density, they are positive loving, they have electron density, they are electron rich, that can donate an electron pair to an electrophile. They are often negatively charged or have a partial negative charge. Okay, and they can be also neutral as well. Okay, that means nucleophiles are attracted to regions of low electron density. Examples of nucleophile includes carbanions or negatively charged ions like Cl negative, Br negative, NO2 negative, OH negative, even H negative, etc. They are nucleophiles. They can be neutral as well, right? They can be neutral as well if they have lone pairs like NS3. So lone pair containing or also can act as nucleophiles because they can donate electrons. No? They have they are electron rich actually. They are electron rich. Let's move to some common types of organic reactions. So you can see substitution, addition, elimination, and rearrangement. So let's begin with the substitution reactions. You can see substitution reactions. Substitution means like in the previous grades we have understood like double displacement, displacement. Similarly, substitution reactions are chemical reaction in which an atom or group of atoms is replaced, is substituted by another atom or group of atoms. In organic chemistry, substitution reactions are commonly seen in reactions involving halogens, such as substitution of hydrogen atom with a halogen atom. You can see the example like C2H5OH. This is ethanol, eth plus N plus ol, ethanol. And Cl negative is attacking like this. So OH negative is removing from here. So you will get nucleophile is attacking and the removal of nucleophile is taking place. So nucleophilic substitution reaction. This is an example of nucleophilic substitution reaction where an electron rich nucleophile like Cl negative and there is a leaving group like, because OH negative is also a nucleophile but it is leaving here, so you can name it as a leaving group. Okay, So the attack will depends on the leaving group tendency, the attack of nucleophile strong or weak, like this. Okay, it's an important reaction in organic chemistry and widely studied in this JEE exams. Okay, like you can see, this is the electrophilic substitution. Okay, so here is the electron density and it will attach this Br positive and you will get bromobenzene plus H positive. So Br positive is replacing the H positive from this benzene ring. So you will get what product, and this is an example of electrophilic substitution reaction. What about the types of nucleophilic substitution? It should be two types, like SN1 and SN2. SN1 substitution nucleophilic unimolecular, one for unimolecular. That means in starting only one molecule is here in the reactant side, right? And in SN2 you can see it should be bimolecular. That means in starting two molecules are there. Okay, in SN2. SN1 substitution nucleophilic unimolecular mechanism. The reaction occurs in two steps. First step is the formation of cation. Like you can see, suppose we have CS3 and CS3 attached with OH and or Cl or anything, right? Let's suppose Cl, tertiary butyl chloride, and any nucleophile is coming. Okay, then you will get, I am writing here, this is Cl. So first step is removal of this leaving group or formation of carbocation. Then the second step will be attack of nucleophile, right? You will get, this is tertiary butyl chloride, this is tertiary butyl carbocation. Then this tertiary butyl carbocation is sp2 hybridized, it becomes planar, trigonal planar. Then there should be two possibilities, and then I will go, we are not going with stereochemistry right now. So there will be two possibilities, like above the plane or below the plane. You will get a mixture, right? 50-50% with 50-50% composition. Okay, you can see the nucleophile comes and will attack on this positively charged, and you will get again sp3 hybridized carbon, like this. Okay, and retention will takes place. Okay, retention will takes place. Okay, so let's move to the next part. You can see a formation of carbocation intermediate by the departure of the leaving group. The next step will be nucleophilic attack on the carbocation by the nucleophile. SN1 reaction occur mainly in tertiary substrate because tertiary carbocations are more stable than secondary than primary. Okay, and proceed by carbocation intermediate, as I told you already. In this mechanism, in SN2 mechanism, it is a bimolecular. The reaction occurs in a single step and it is like a backside effect. Okay, it is like a backside attack. Suppose carbon and there is a hydrogen, there is a hydrogen. If more crowding is here, so the reactivity and stability order for SN1 depends on the stability of carbocation, but for SN2 it depends on the crowding. That means the steric hindrance. In chemistry we can say the crowding word as a steric hindrance. Okay, and you can see it there should be like chlorine. Then nucleophile comes and attacks majorly from backside, like 180 degree. Okay, and it will attack like this, and it is like a concentrated reaction. That means in a single step it is taking place. Okay, then there will be a transition state like this: carbon, hydrogen, hydrogen, hydrogen. This bond is breaking, simultaneously this bond is forming, this is forming, this is breaking, and then this is like a transition state, and then you will get compound CH, and it should be nucleophilic attack. Okay, then this is what, this is like a inversion of configuration. So the nucleophile attacks the electrophilic carbon at the same time as the leaving group departs. Okay, this is like inversion of configuration. Then you can see factors affecting the reaction: steric hindrance, nature of the leaving group, nucleophilicity. As I told you already, like steric hindrance, SN1 reactions are favored in substrates with the high steric hindrance, because if high steric hindrance, more alkyl groups are there, then that allow the leaving group to leave easily, and they will stabilize what? They will stabilize the, what we can say, they will stabilize the carbocation as well, right? If they are electron donating groups. SN2 reactions are favored in substrate with low steric hindrance, right? In SN1 reactions, if they are electron donating groups attached to the carbocation, they will stabilize the carbocation with the plus I effect as well, right? With plus I or hyperconjugation they can apply if they are CH3 groups. Okay, that's the point. And SN2 reactions are favored in substrate with low steric hindrance as it allow the nucleophile to attack easily. Next, nature of the leaving group. The leaving group should be a good leaving group such as halides or sulfonates for efficient nucleophilic substitution reactions. Nucleophilicity, the nucleophile should be strong nucleophile to efficiently replace the leaving group. If the nucleophile that is attacking, if the attacking nucleophile is not strong, so the reaction may not takes place. Okay, and the nucleophilicity depends on the factors such as charge, electronegativity and solvent effects. Okay, next, electrophilic substitution. Same like nucleophilic substitution, in this case electrophile is substituting. In electrophilic substitution reactions, an electrophile replaces a hydrogen atom in an aromatic compounds. Like this is an aromatic compounds, benzene, and each carbon contains one hydrogen, and suppose there is an attack of Cl positive, you will get what? Chlorobenzene. That means the replacement of this H positive and attachment of the Cl positive shows that this is an example of electrophilic substitution reaction, right? Common example include the nitration, halogenation, sulfonation of aromatic compounds. Then addition reaction. In addition reaction, you can see here introduction of addition reactions are chemical reactions in which two or more reactants combines to form a single product. Okay, like you can see this is CH2 double bond CH2 ethene plus HBr. So no removal of any side product is here. There is only addition. That means hydrogen is added here and Br is added here. In organic chemistry, addition reactions are commonly seen in reaction involving alkenes and alkynes, right? I mean to say multiple bonds. So in what I can say, ethene plus HBr, you will get bromoethane. That means this is the addition of hydrogen and halogen, right? That means hydrogen halide. Okay, that means hydrogen bromide. Okay, you can see electrophilic addition. In electrophilic addition reaction, an electrophile reacts with a nucleophile to form a new bond. Electrophile reacts with a nucleophile to form a new bond. Common examples like addition of hydrogen halides, the previous one, right? X. Okay, halogens like Cl2 and water like H2O to alkenes. Okay, that means the electrophile reacts with a nucleophile to form a new bonds. Nucleophilic addition, nucleophile reacts with an electrophile to form a new bonds like Grignard reagents RMGX. Grignard reagent is RMGX. Organolithium compounds, cyanide to carbonyl compounds, etc. Next type is elimination reaction. In elimination reactions, as the name suggests, elimination is taking place. That means removal. So these are the chemical reaction in which a molecule loses a small molecule such as water or any gas like or hydrogen halide to form a new product. Like you can see CH3 whole to thrice COH. This is tertiary butyl alcohol. This is the structure CH3 OH CH3 and CH3. Okay, and you can see hydrolysis is taking place and heating. Then you can see it will form 2-methyl prop-1 with the removal of water molecule. With the removal of water molecule, how will the reaction takes place? We will be discussing in the upcoming classes. But the point is here, right? This is elimination reaction because there is a removal of a small molecule such as water molecule, right, to form a new product. And in organic chemistry, like elimination reactions are commonly seen in reactions involving alcohols, alkyl halides. That means RX or carbonyl compounds. Carbonyl means like C double bond O compounds. Okay, aldehyde or ketone. There are two types of mechanisms like E1, E2, right? Majorly E1 stands for unimolecular elimination like SN1. It is a two-step process like SN1, and first the steps are different. Ionization of the substrate, first step, to form a carbocation, followed by the loss of a leaving group and formation of a double bond. E1 reaction proceeds by a carbocation intermediate like the SN1 and favored by weak bases and polar solvent. That is the main point here. Weak base and polar solvent. E2 elimination stands for biomolecular elimination. It is a one-step process. Okay, one step. Similarly, like SN1, it is a two-step process. SN2, it is a one-step process. E1, it is a two-step process. E2, it is a one-step process. There is a E1 CB as well. Okay, it is a one-step process. Simultaneously removal of, like in SN2. Simultaneous removal of a proton and leaving group to form a double bond. E2 reactions occurs with a strong base and are favored by high concentration of the base. Okay, so this is example like dehydration reactions involve the removal of water molecule from a molecules, like removal of H2O includes the dehydration of alcohols to form alkenes. Okay, next dehydrohalogenation also involves the removal of what? Hydrogen halogen. Common examples like dehydrohalogenation of alkyl halides to form alkenes. Okay, like beta elimination. Next one is rearrangement reaction. Introduction of rearrangement reaction. Rearrangement reactions are chemical reaction in which the atoms in a molecule rearrange to form a new molecule or isomer. In organic chemistry, rearrangement reactions are commonly seen in reactions involving carbocations. For example, there are two types of rearrangement reactions like hydride shift or methyl shift. Hydride means H negative shift or methyl means like CH3 shift. Okay, you can see here the hydride shift involves the migration of hydride ion from one carbon to another, right? Occurs during carbocation rearrangement. For example, suppose if any time you will get this type of carbocation CH3, CH, CH2, positive and CH3. So what happens? You can see there is a hydrogen, right? There is a hydrogen. So this hydrogen will migrate to this carbon. That means 1-2 migration, 1-2 hydride will hydride shift will take place, and you will get CH3, C, CH3, CH3 and positive. So this is primary and this is tertiary. So hydride shift will take place when there is a conversion of primary to secondary, when there is a conversion of primary to tertiary or secondary to tertiary carbocation. Okay, like this. Next, methyl shift involves the migration of a methyl group from one carbon to another. It also occurs during carbocation rearrangements. For example, CH3, C, CH3, CH3 and CH2 positive. If I will rearrange this methyl to this, that means 1-2 methyl shift. So you will get CH3, C, CH3, CH2, CH3 and positive. So this becomes, this is primary carbocation, this is tertiary. Again the same point. Okay, so let's discuss the relevancy, that means some important questions for JEE exams. Which one of the following is most stable, right? So which one of the following is most stable? So you have to apply all the concepts that we have discussed today. You can see this is like allyl carbocation, this is normal like carbocation, right? This is again allyl carbocation. This is there is an electron withdrawing group, there is an electron donating group. So you can see due to the presence of electron releasing donating group CH3 and resonance effect, this is more stable. This is more stable. This is like this, then positive comes here and this positive can be what I can say stabilized by this CH3 due to this electron releasing nature. Okay, the order of stability of the following carbocations, again you can see this is allyl carbocation, this is normal primary carbocation, this is benzyl carbocation. Definitely benzyl carbocations are more stable than allyl carbocation due to conjugation like this. Okay, and this is due to primary inductive effect, this is due to inductive effect. Okay, plus I effect is taking place here. So what is happening? Definitely 3, then you can say 1, then you can say 2 will be the order. You can see the answer. You can see the order of stability of carbocation should be benzylic carbocation more resonance stabilized than allyl, which is resonance stabilized, then propyl stabilized by plus I effect. So 3 1 2 3 1 2, you can check the order. 3 1 2, option D is the correct answer. The most stable free radical PHCH2CH2, you can see PH is phenyl, then this is CH2, then this is CH2 radical. This is not benzylic radical. Then methyl and CH2 radical, then Me2CH radical. Okay, this is primary radical, this is secondary radical, and PHCHMe. Okay, this is radical. So PHCHMe, that means PH, this is CH radical, this is Me. Okay, this radical is stabilized by this benzene as well as this methyl group. So you can see the most stable free radical is secondary benzylic radical, right? This is like secondary benzylic radical, this is primary benzylic radical. Okay, this is like secondary benzylic radical CHMe. Okay, this is like secondary benzylic radical, and if I will attach benzene, carbon, methyl and radical, this is like tertiary benzylic radical. Okay, so PHCHMe due to resonance, secondary benzylic radical is more stable. Next, among the following, the least stable resonance structure is, definitely you know very well the rules of resonance. So the least stable resonating structure is A. 2 positive charge present at the adjacent place elevates the energy, increases the energy and lowers the stability. You can see here 2 positive charge separation is must. Charge separation is must. You can see charge separation, right? You can see charge separation. That is the point here. So option A is the right answer. The order of stability of the following carbocations. So we have discussed this. You can see the next, arrange the carbon ions. So you have to complete this question as an homework. Okay. Next, arrange the following free radicals in order of decreasing stability, like methyl, vinyl, allyl, benzyl. Okay. And on the basis of hybridization and regeneration effect, the correct order of bond length of the following is, so you have to 1 2 3 4, these are the bond lengths. Okay, these are the lengths of these bonds. Okay, so you have to check the answer. The correct stability order for the following species is, so again you have to check the stability order according to the effects, electronic displacements, or whatever the concepts we have discussed today. The next is, which of the following resonating structures of 1-methoxy-1,3-butadiene is least stable? Least stable structures, charge separation and other rules you have to follow. Okay, so this is the end of this class. Thank you so much.